possibly wrap up with the Athena tutorials. In the last one we did the 3D Rayleigh-Taylor instability, and in this one we'll just kind of see what we have left, I suppose. So to start with, we're going to go to Athena tutorial MHD, and it should be the very first link up at the top. It's Princeton University.github.io/Athena-C version. I'm going to click on documentation, click on tutorial, and then we finished 3D MHD last time. Try with parallel processors with MPI. So this is a big step. You basically need to run with multiple processors when you do 3D simulations at any even at fairly coarse resolutions, especially if you want to do scientifically meaningful research at higher resolutions. Okay, so we're gonna saying to go back and do a configure command, and so all of this is kind of standard. This --enable-MPI is the new part. So we're gonna open our terminal. That's a pre-existing window. We're gonna open a new window for the terminal, and we're gonna make this a little bit bigger. We're gonna go to so in probably the first video showed how to write this SSH MPI alias. I need to grab my phone and do a two-factor authentication step. And now I have to enter my real password. Okay. And then I previously downloaded Athena, untart it in here. I'm going to type in the make clean command that they suggest, and then /configure, because configure is actually a script in this directory that we're executing, with problem RT for Rayleigh-Taylor, with order 3, this is the spatial reconstruction, and then enable MPI, and we'll see if that works. And yeah, so it enabled it. Very good. Let's take a look at module list. So here on this remote machine, there's a module system. I don't actually see MPI on here, so I'm kind of thinking that the compilation step will fail. Okay, compile and link the code against the MPI libraries, right? So for this, we're going to need to take a couple options. You can either use environment variables, you can use your C shell RC, or in our case, bash RC. Hardwire paths using Athena make options.in, probably do that. So let's go take a look at, we're already in Athena. Take a look at make options.in. All right, let's see. So this is a template for source make options. So, okay, so if we didn't want to continuously add in machine equal to Kraken for make options, this is the file that we'd want to edit. All right, and so this is where we can hardwire some paths. So here they do it for Payton-MPI, so we can, let's see, I'm going to just scroll all the way down. So if equal machine Kraken. I'm not exactly sure what the name of our machine is, but I'm guessing if I just type in machine equal to Kraken MPI, I'll do -MPI to match the syntax for Payton. And this is not actually Kraken, but it doesn't matter because we're telling it, Kraken. All right, so we'll do else if EQ money machine. So this $ says to expand whatever is here. So this is a shell variable, which is assigned a value of Kraken-MPI. And so that's saying, okay, actually use that value that's stored in the variable. And we're checking if this variable is equal to Kraken-MPI. So I mean so the main reason to do this is because this whole if-else sort of loop ends in an else and then aborts if none of these are found. I mean, we could just write this statement in the else, honestly, and remove the abort. or we could just erase all of this if else, but just going to go for kind of minimal modification. Okay, so we need our C compiler, our linker, which apparently is the same as the C compiler, opt, O3 is fine. I'm trying to remember, but I think -G is debug, which is useful for debugging, but I don't think we want it. MPI include, MPI lib, and then some FFTW stuff. I don't think we need the FFTW. It is nice to have. So let's try to find some of this stuff. For University of Michigan's cluster, it's really easy to find stuff. But I don't know as well how to find stuff here. So if I just type module, maybe it's module search, and then I can try MPI, and maybe that worked this time. Yeah, okay, so we got some stuff. So there's an FFTW, MPitch, and HDF5 and HDF5. Let's see, MPitch. I'm gonna go with OpenMPI. I like OpenMPI. All right, so we're gonna do module load, and it's probably not gonna work because it's probably gonna, oh, it did work. I thought it'd maybe require some other stuff, so I'll try which MPI CC, and so that's nice, it expands it there. And so rather than hard coding it in to make options.in, I'm just gonna use MPI CC like they use just wherever CC is pointing. And LDR, also going to set to MPI CC. Do an extra space here to keep things lined up and pretty. Do opt, I'm just going to do O3. So for optimization, when you're compiling in C, I think also, yeah, Fortran code is the same. This is the optimization order. So order 3 is the highest optimization order, at least at the present time. And so this will do all your fancy stuff like loop unrolling and et cetera, et cetera. Order 2 is like sort of a medium optimization. It can actually be faster than O3, depending on kind of what is written in your code. Generally, O3 is fastest, but it depends. Certain things where O3 tries to optimize can actually slow things down, and also typically creates a bigger executable. So if you're kind of memory limited, then sometimes you need to go with O2 or O1 even. And then O0 is the lowest order, and that's also very useful for debugging because it does things as you'd more have expected to look like. Okay, and then MPI inc is this MPI include. So we need this -I, and then so this which MPI CC is also useful for finding the include directory. So it's typically the same up to the bin. And then if we look in here, there's the bin folder, which has the binaries or executables. There's an include folder as well as a lib folder. So that include is what we want. So if we go back to makeoptions.in, well, I forgot it already. But again, it's just this part and then include after that. Okay, so I'm gonna copy that in, but it's really important to only have one slash, and there needs to be no space between this capital I and the beginning of this. That's important. And then for MPI lib, it's pretty similar to include, and this all needs to be cap locked. Like you need to match the case exactly here. This isn't Fortran, unfortunately. So it's just the same except it's lib and then -L MPI. So this is saying to like link all the MPI stuff. Okay, and then there's some FFTW stuff. We're gonna skip that because I didn't load a FFT module. We can, I guess, do module search, FFTW, and there probably was a bunch of stuff. So ideally we want to find an FFTW, I think that's compatible with OpenMPI, whereas I'm seeing MPitch as well as MPitch Intel. So I mean, we could always switch our MPI version to one of these, but I'm not going to worry about FFTW, so that should be fine. All right. And then I don't think that they actually did the make unless they mentioned it somewhere else. Yeah, need to run configure again. All right, well, yeah, that's kind of weird. So run configure with problem RT with order 3 and enable MPI. All right, and then so that generates a make options file from the make options.in. And so we see that we have machine set to Kraken MPI, and then we have our Kraken MPI set up here. So sweet, that worked. All right, and now if we do make all, that did not work. So why did it not work? Missing endif. Okay, interesting. So let's take a look at makeOptions.in, which is where from which the makeOptions file is generated. So we have if equal to else, if equal to else, if equal to else. Maybe there's a whole bunch of endifs at the very end. Yeah, there are. And so we added one additional if equal to, and so I guess we needed to add an additional endif. So that changed it for makeOptions.in, but we already did the configure, so we could reconfigure, or we can just add an endif over here. All right, and then let's try make all one more time, and now it is compiling, so sweet. And so that'll take a few moments, but you can see that, so in comparison to previously where I was using just like some C compiler, I mean, this is still a C compiler, it's just an OpenMPI wrapper, which basically helps the C code communicate between different processes. All right, and it's done, so that's sweet. And so if we scroll down here, they want to copy a file. So we're going to cd into our runs folder that we made last time. We're going to maker-p rt-mpi. We're going to copy from the bin folder, the new Athena executable, and copy that into rt-mpi. And then we're going to copy, sorry, the same path that they're showing, test 3D mhd at input rt. And they're saying to rename it and to athinput.new. So okay, we can follow that. Maybe I think maybe it would make more sense to call it athinput like .rt-mpi, but we'll just call it new. So go to rt-mpi, and they want to change the decomposition of the grid, right? So they're gonna use different sections of the grid for different processes. And so if we look at that, if we look at the athinput.new, go to domain 1. Let's see, domain 1. Okay, so we got level and x1. They want to add, I'll just add it to the bottom, I guess. N grid x3 equal to 2. So that just divides it into now 2 blocks. And they're pointing out if you want to have like 8 blocks, then you'd set n grid x1 equal to 2, x2 equal to 2, x3 equal to 2, because 2 times 2 times 2 is 8. All right. And then, yeah, so I guess so they're running with 8 processes, so we probably want to decompose this as many as there are processes. So do x1, x2, x3, and then we'll do the MPI run command, np4, np8 rather, and Athena /Athena -i at input.new, and they want to set the time. I don't like doing this on the command line, but I didn't modify the input file, so we'll just do it. All right, and then that's running, and so this should theoretically be 8 times faster. Yeah, so this kind of walks you through it textually. So if you're a visual learner, hopefully this video helps. If you're more of a textual learner, you can just actually read through the documentation. Probably doing both are useful. All right, so this is running through. It's going to take a while. And yeah, so the kind of tricky thing about running in parallel now, so we have to SSH back to the remote machine, cd into Athena, go into our runs, rt-mpi, is instead of dumping all the outputs at this level, it creates a different output folder for each processor. And so this is honestly terrible for a file system, especially if you generate thousands of files for each processor. And if you're running on tens of thousands or 100,000 processors, it's systems administrators will not like you. They did better. And so, I mean, the reason why you do this is because it means that you have perfect scaling for outputting. Whereas typically, when you try to get massively parallel, file outputting becomes a problem because it takes a while to communicate the whole grid onto one processor, which then needs to have enough memory to hold the whole grid, and then write the file, or write the file in parallel. But then, and that can speed things up, but there's still a bit of overhead there because they have to make sure that the processes do not conflict with each other. So anyway, so yeah, it's barely advanced, but it's at least gone one step, generated one output file in addition to the initial dump. And so this is saying that there's this join vtk.c file. So if we go up and we're still in the runs directory, and now we're at the root Athena directory, there's this viz folder, vtk, join vtk.c, we'll copy it on over here. And then to compile this, we'll use GCC. Maybe it'd be useful to use MPI-CC since that's what we use, but I don't think it matters. So we'll just use GCC -o join vtk.x for the executable name, and then the name of the file that we're actually compiling. And so this is equivalent to optimization order 0, so this could be kind of slow, but we're just joining output files, so I don't think it's that big of a deal. Probably for if you do high resolution, you might want to do this a bit more efficiently. GCC is also typically slow compared to, for example, an Intel compiler is typically fastest if you're running on Intel cores, which a lot of clusters are these days anyway. All right, so that generated this join VTK executable, which is green. So yeah, in our current color scheme, regular files are white, directories are this blue-purple, and executables are green. You can also see that with ls-l. There's this D sort of space for directories, and then executables have this execute option, whereas regular files you can read and write if you have the right permissions, otherwise just read. Okay, so enough explanation for that. I'm not probably going to remember exactly the syntax of this join vtk.x command off the top of my head, so I'll cheat and go look at where I've done this before on Freya. So I'm just going to log in, and I had a typo, I guess. And I'm going to go to the Scratch side. I'm going to go look at Athena MHD. I'll look at, I wrote this merge output script. So maybe I'll just use this, but I think I'll just kind of talk through it because it's really a pretty short script. So the main thing is that you do /join vtk.x-o, the name of the output file, which we are putting in a merge directory. So I'm going to make dir-p. Well, don't have to do the -p because I haven't done it before. And then /join vtk.x-o, the name of the output folder, also kind of the path. So we want to put it in this merged folder so that this home sort of level doesn't get cluttered. Then we're going to call it, I don't remember, probably doesn't matter too much, but we call it ID cloud or just whatever the name. So we'll do rt-mpi, and then we'll just do 0, maybe. We'll do 1, 2, 3, 4. So this will probably match the name in here. So Yeah, so we're going to merge the Zira files together. So we'll just match the same naming convention. So we'll actually just do rt.quadruple0.vtk. And then, so this is the output name, and then the inputs are ID star or ID question mark. So this is again a wildcard, so it'll match any of these. And slash rt.1234.vtk. I think I can just hit enter, but let's see if there's anything else. Nope, that's it. So if I hit enter, then it merged them together, and so now we have a single output file that we can plot with. So I'll cd in here. Oh, maybe I'll write it. Maybe I'll just copy the plot script that we used previously, and then I'll tweak it a little bit. So it's going to be pretty similar. Now we'll actually use OS and do os.cheddar, this is change directory, into merged. And then otherwise it's going to work exactly the same. And it takes a moment to load it, and then it's going to do the slice plot and save it. And this should look pretty similar to what we had last time, or should look exactly the same as last time. So let's see. Well, that doesn't look quite right. All right, so this is probably only showing a section of the domain. It's also possible that I messed up the input file somehow. So we'll look at athinput.new and just see if there's anything sort of obvious that looks wrong. So level 0 and x1 64, and x2 64, and x3 128. We have nx1 equal to 2, and x2 equal to 2, and grid x3 equal to 2. And so that's what they also had. Yeah, that should be fine. Could be that I merged it wrong. Okay, I guess one thing I'll try is I will try, instead of slicing along the y-axis, I'll try slicing along x. I'm guessing that this is an issue with the merge that I just did. But we'll try plotting again. And it's going to take a moment. Okay, display, what is it? Merge display. Okay, all right, because that's in the merged folder. So that's why the tab complete was not working. It's going to look exactly the same. It's just that the noise is on the other thing. So this is only showing half the domain is the issue right now. Whereas in terms of the values along Z, it looks like that would be correct. Although this is times 10 to the minus 2. That's interesting. So this is actually going from like 0.05 up to 0.05. Similarly along Y, that's going from like minus 0.025 to 0.025 or something like that. So if I look at the input file again, is that what I'd expect the dimensions to be? Oh, it's not one level up, it's here. I guess I'm getting a little tired. Yeah, okay, so that seems reasonable, or not unreasonable. Actually, wait. This was only showing half of it, right? Yeah, because I just mentioned that it was going from minus 0.025 to 0.025. So, probably did not merge it correctly. So I'm going to look at this merge script one more time. Well, no, that doesn't matter. So over here, I just had all the ID folders in an out folder. And I'm just wondering if I missed half the files somehow. So we're just going to delete. We'll just delete everything from in there. Then we're going to try this merge again. So /join vtk.x -o. Then the output file name, so merged rt.1234.vtk. And then the input file name, so id, we'll do star. And then star.vt, well, star.1234, is that right? Yeah, should be star.quadruple 0.vtk. So we're merging it again. I'm wondering if it's just an issue with that like initial file. I can also actually read what it's doing. So it looks like it's going into all of them. So it went into ID0, ID1, 2, 3, ... all the way through 7. So that looks like it would be fine. We'll do a plot. Well, let's see if this is. So this is cheddaring into merged. It's globbing the VTKs and then it does the plot. So that should be fine. It takes a moment to load it. Okay. Display merged. Let's see if this is any different. Okay, now it's better. Yeah, so the previous merge failed for some reason. I guess I probably was, I don't know. So let me just check by going up. So this was the one that worked using the asterisk. So I'm guessing I was missing one of these decimals. But let's just take a look at my previous merge command and try to see. It can be really hard to see typos though. Yeah, I don't see anything evidently wrong with it. So I guess maybe are these not RT? So if I go LSID, I think it would be RT. Yeah. Darn it. So it looked fine to me, but I had some sort of subtle typo here. And that was fixed with the asterisk. So I guess asterisk wildcard can be nice sometimes. Okay. So yeah, so that goes into how to do this with MPI. And then I think that so this is using visit, and so this is really nice, and visit is really easy to use too. It's a GUI-based method. YT is nicer for scripting. I mean, you can also script in visit. Oh, and also visit can just auto-merge them, so that's super nice. Visit's by Lawrence Livermore National Lab, I believe, so it's a pretty nice piece of software. And then we can take a look at static mesh refinement. Main thing is just in this configure line, you're going to add enable SMR. And so this just allows you to get more resolution where you want it. Now, the downside for SMR, this static mesh refinement, as opposed to adaptive mesh refinement, is for static mesh refinement, you need to tell the grid exactly where you want it refined. Whereas adaptive mesh refinement, I mean, you still tune the algorithm to ideally not over refine as well as not under refine to really detect your features of interest. But in general, like once you have it set up, I think it works, pretty well. For static mesh refinement, I mean, the plus side is it's cheaper numerically than adaptive mesh refinement because you're just presetting things rather than computing things on the fly. But the downside is, especially if you have a very dynamic problem where you don't know where the features of interest are going to be, then you end up throwing more cells at something than you'd like. A plus side of SMR is you can use it to do kind of an effective uniform grid and just have like some extra space before you get to the boundary to some extent. So you can have like a uniform grid, high resolution region surrounded by a box of lower resolution, which kind of spreads you out before you reach the actual boundary condition. There is a bit of a refinement jump and therefore almost acts as a boundary condition, but in any case, so this is useful but not required for our present purposes. All right, so that goes through all of the Athena tutorials. Now know how to do the basics with Athena, And of course, the nitty-gritty part comes to actually defining a problem and running on tens or thousands of CPUs using a job submission script like PBS, like Torque with PBS or with Slurm. And so maybe we'll jump into that next time. Okay, bye.